many thanks to the organizers for the invitation. I've been here many times, but many things have changed during the last years. This is joint work with 3 of my PhD students, namely Fabian Altekrüger, Paul Hagemann, and Johannes Hertrich, and 2 colleagues from the University in Bremen, Alexander Denker and Peter Maas. And sorry for don't having photos of them, but you can be sure they look very nice. The talk is split into 2 parts, more or less. It's about normalizing flows, both parts. And in the first part, I will just introduce normalizing flow, what they are doing, and I will show just how we have applied them in image processing. And then I will go to a part, normalizing flow has a drawback, namely they have a low expressivity if you bound the Lipschitz constant, and then you can somehow solve this problem by introducing so-called stochastic normalizing flows. And this is the second part of my talk. Okay, so what are normalizing flows? I will deal with so-called generative neural networks. Generative means that I want to produce samples of a where is the pointer here? Samples of a high-dimensional probability distribution. Even if I know the density function, you cannot sample from such high-dimensional things, except you have a very simple probability density like the Gaussian. And that's why people try to construct neural networks. And then they sample from this latent distribution, which is very simple, a Gaussian. They take one sample and they construct a network in such a way, if they apply this network to the sample, then they get one sample from the other probability density distribution, okay? So you generate a distribution. So in the first things in this direction where this generative adversarial neural networks, I will not speak about this topic. Then variational autoencoders come into the play. This will be one part of my talk. In the second part, with stochastic normalizing flows, the main topic of my talk are so-called invertible neural networks. And here there exist different architectures. One architecture are so-called residual networks. Here the invertibility, I want networks now where you also have the inverse network, which you can invert. No? So in these residual neural networks, they work more or less with Banach's 6-point theorem, and they are not directly invertible in this sense. I'm interested in so-called directly invertible neural networks where I can write down the inverse immediately without having iterations. So, and you will see it in a minute how this works. And I have to say that I'm dealing with discrete normalizing flows. You will see why. And there exists also a continuous variant of this normalizing flows. We have an overview paper on this where we have shown the relation between these discrete and continuous normalizing flows. And here is another overview paper of Lars Russotto and Eldad Haber, where you can see how this works. This works then with PDEs, and we can interpret our things as discretization in time of this in the PDE of this ODE. So, okay, let's go ahead. Okay, just first I tell you what are these normalizing flows. As I said, it's a neural network with some parameter theta, and indeed it's a whole chain of neural networks, namely these guys here, T1 to TT. And this T you can imagine as a step size discretization. So this P corresponds to a step size discretization in time. But this is just for if you have continuous normalizing flows in your brain. So, and I said they are directly invertible, and this depends on the structure of these networks here. Namely, you split your income, your latent variable, into 2 parts. Later we will deal with patches, and we split them into 2 parts. And then we write down this network and write it down in such a way here. These are just, again, the variables. You see I put Z1 and Z2 inside here, and then I get the first output, and the first output is again here. And where is the neural network? The neural network is in this S and in this T. These are shallow networks, one latent, one layer or so, so they are very small, and they are here. So, and why this guy is invertible? Not because I want to invert the networks, S and T, they are not invertible. I invert the structure here. Yeah? I invert this Z1 e to the power of something, and I can immediately write down the inverse of this guy. This is just the same here, but you see these are the same networks. I don't invert networks, I invert the structure. Yeah? So, okay. Now I want to use these networks to sample from a high-dimensional probability density, and now I need some loss function, how to train these networks. So, and here the idea is as follows, namely, this is my distribution where I want to sample from. And I say, okay, this distribution should be the same as the following. I apply, this is where I want to sample from. I apply my network, my inverse network, t to the power of -1, and then I take just the simple probability density or distribution here, like the Gaussian. So in this t to the power of -1 times p set, which is the push forward of p set, should be very near to the distribution I really want to sample from. That's reasonable. So I have to train it in this way. So the only thing I need is now, these are two measures, and I need a distance function between measures. And now you can take what you want, take Wasserstein distances, take TV distances. Usually, and what also we did, is we take the Kullback-Leibler divergence. So, and how this Kullback-Leibler divergence is defined, we want to learn now our function here, our network T, in such a way that these guys are near to each other. And near means Kullback-Leibler is just the integral. And if we assume that these densities, that these distributions have density functions, which I denote by small p now, then this is just the definition of the Kullback-Leibler divergence. So now you see here the density functions, a logarithm in front. So logarithm of a quotient means you become here a minus. Then you see what I want to learn is this network T. This has nothing to do with my T, so I can skip it if I want to learn it. And I just can take this as a loss function. And then there, between these push-forward measures, there exists a transformation formula. That's just what you learn in analysis 3. And or maybe in France in analysis 1. So you plug this transformation formula in, and just consider the second part here. You plug this in, you have a logarithm here again, and a product of two guys, and again, because it's a logarithm, this becomes a sum now. So, and then you apply that you know this, that you know your latent distribution. For example, you want to sample from the Gaussian, and then you can plug this in, and this first part here is just now an expression like this. It's just your network, and there are two numbers respect to this probability density, which is written here. And this is just the second part. And then you can apply your favorite algorithm, like stochastic gradient descent, or what we have used, if you add here some additional regularizers, was an inertial stochastic Palm algorithm, which we described in a paper together with Johannes Hertrich. And then we can really find a gradient descent algorithm to find some minimizer of this loss function. Good, so far so good. We will see how this works and how we want to apply this. But because we had it yesterday in a talk, there was also already described the Kullback-Leibler distribution. Let me say one word about this Kullback-Leibler distribution. Okay, Kullback-Leibler or divergence. Yeah, Kullback-Leibler divergence is not a distance, it's just a Bregman distance. And Bregman distance here means that this guy here becomes indeed 0 if and only if we have to the left and to the right the same measure. That's completely fine. But it doesn't fulfill a triangular inequality, and what's more important, it's not symmetric. So you can ask me now, okay, in your approach, you take such a direction here, you take the Kullback-Leibler, here is what you want to sample from, here is what you produce, why you take it in this direction. Okay, it works, we need it in this way, but what happens if you change the arguments here? If you put this in front and this in the second position? And this changes everything. Namely, it changes what you have to learn. You will later see in my talk that I will use it for inverse problems, and it depends. If you take this, you should know the operator of the inverse problem. If you take this, then you don't need it, for example. Yeah, you can, if you go ahead, as it changes many things. So the second thing is the properties of this loss function. Namely, Kullback-Leibler, I made it a little bit fast, is only defined, Kullback-Leibler, between px and py, if the first argument, is px, is absolutely continuous with respect to py. Otherwise, it is plus infinity. So, and this means, if you have it in this direction here, this guy must be absolutely continuous with respect to this guy. That means if you have areas where this measure is not supported, has an empty or is 0, then this must be also 0, because you have a quotient here. So if this is 0, this must be also 0. Otherwise, the quotient is not defined. And this leads to a property which is called mode covering. That means if you learn such a function, it can appear that you not only sample something from your blue probability, but you generate artificial samples, which which you don't really want. So, and you have the opposite direction. If you change the arguments here, then this guy has to be absolutely continuous with respect to this guy. So this must be 0 if this is 0. And this leads often to mode-seeking things, namely that the blue guy, or that's the red guy you want to produce, covers one mode, but this is enough. It must not be the second mode. And this is mode seeking, and you have a mode collapse in such algorithms very often. But nevertheless, I take the first one, and there is another paper which works with Wasserstein distances. And in this paper, for example, they need exactly this Kullback-Leibler divergence. No? So just a word about Kullback-Leibler. You have to be careful in which direction you take these arguments. So, but we take this one, okay? So now we have seen which loss function we have to minimize if we take this function. So now let me come just to applications, and later, as I say, I will go to some math again. So what are the applications? We want to apply this normalizing flows with this loss function somehow in inverse problems. So in an inverse problems, normally you have an operator f, which is ill-posed. You apply it to some x, and then some noise comes into the play. It can be different noise. Usually it's not Gaussian, Poisson noise in computerized tomography, and you get out an y. So, and people in inverse problems and in Bayesian approaches, they solve it by minimizing not just the distance between this f of x and the y, because then you will have all the noise again, but the one has to add a regularizar. It makes the problem well-posed if you think in terms of inverse problems, or you can say this is an image prior, where you can put all the prior knowledge which you know on your images into this image prior. Yeah? And then it comes more from a Bayesian approach. I will have it on the next slide. So, okay, what I want to do, I will not touch the data term in this talk. We also have touched this, of course, and learned the operator. You can do anything with these neural networks today, but I will do this. Also, I will not touch the data term. I will only speak about the regularizing term. So, now, if you have been many years in imaging, then you know that the best methods for denoising are not methods like L2TV or any variants of this TGV and whatever exists. I also did this. But the best methods for denoising are patch-based methods and methods from statistics like MMD or something like this. And all these started with papers from Morel and Boades and was later adapted in BM3D, which is still very good in denoising, but this was the pre-learning area where people did many, many things, and we did it also on manifolds here and so on in denoising or other things. But they don't use the whole image. They use probability theory, and they use patches of images. So, and this is exactly what I want to do now. I want to learn this regularizer from patches of an image. Yeah. So, what I would take. The thing is, I don't have many, many images. I want to learn everything from one image, or in CT from 6 images or something like this, from very few images. But I take few images. This J stands for few images, small n, say one image. But I take many, many overlapping patches of these images into account. And how I do this, and this is the next slide, I do the following. This is exactly the loss function we had on the previous slide, exactly the same. This is a loss function which comes from this normalizing flow. And now I do the following. I train now this normalizing flow with, in dimension, I take small patches. These are patches of size 6 times 6. So my latent distribution is the Gaussians in R to the power of 6 times 6 is 36. So, and then I learn a network, I train a network which maps into the distribution of patches. These are 6.6 patches. If you put them in a row, you get a distribution of patches. And I learn the distribution of patches, or I learn in invertible networks which produces this distribution of patches. Okay? So, and I can do this. And then I get some T, some neural network T, which is this learned network. And then I plug exactly this network in my variational method now. Here is the data term. This is exactly the same, but the regularizer is now the regularizer which best forms my patch distribution. So, and this is exactly this regularizer, and then, of course, I have to put my new image which I want to analyze here in this patch distribution. So, now, if I have certain classes of images, I can apply this for different inverse problems, yeah, with a regularizer which comes from this kind of inverse problems. So let's go to my first, one word about this map approach, this Bayesian approach. To come to such an inverse problem here, there is one approach which is called Bayesian approach. What we want to find, we want to maximize this posterior distribution. Then we apply Bayes' rule, we get this, and then you come also to this expression you had on the previous slide, yeah, this Bayesian, so-called Bayesian approach. So, and what you need for this, in order that it is a Bayesian approach, is that this guy is the logarithm of a probability density function, or with other words, you take the logarithm, if this is an exponential of something, this guy should here, this exponential should be in L1. And indeed, we can show that our patch regularizer is such a guy where this is indeed in L1, if I suppose that my network is Lipschitz in one and in the inverse direction. So then it's really a Bayesian approach which I'm doing here. So, and we have two things which are nice, namely sparsity of training data. I don't need many training data, you will see it in a minute, but data from the problem. I don't want to learn your knee or your some lever in CT by faces of celebrities. This is not my thing, what I want to do. Yeah, I want to learn it from CT images. So, and the second thing is you will also see that I have now a flexibility here in incorporating different operators in the data term. So let me go to computerized tomography. So I don't explain what it is. I think everybody knows it here, what computerized tomography is. You have also this linear operator. We have Poisson noise, and the data term comes from this Bayesian approximation with this Poisson noise. So I don't touch the data term. I have to construct the regularizer, and we learn the regularizer from 6 CT images, which we take from a data bank from Peter Mars. So, and these are the 6 images we learn from, different images, but CT images. CT images are a little bit special. It seems to be a little bit blurred. Yeah, I don't learn from celebrity faces. So, okay, and then we can do different things in this computerized tomography. For example, low-dose tomography, where you have only very few angles here. Yeah, then this A has very few angles inside. Or limited angle tomography, where the angles are in a certain area, say in an area from 0 to 36 degrees, and some angles are missing in this computerized tomography. So you can do CT with different operators, A here. But the operator is only in the data term, not in the regularizer. I can take the same regularizer because these are my example images where I learn the patch distribution. So here is the result, which you can see what our algorithm does. So I make it, this was low-dose tomography. And you see, these are algorithms where you don't have many patches, where you don't have many images, where you don't learn from many images. Filtered back projection, of course, doesn't work for this limited angle tomography. This is just a deep image prior. EPLL is the Gaussian mixture model, works with learning Gaussian mixture model. This is nothing with learning. You learn a mixture model, but not a network. And here's not another method. But you see, if you compare this to our patch in R, that, it's not comparable. We are much better because we have some prior images where we learn from, but only 6 of them, not a lot. So, and this is another thing where you say, okay, this looks a little bit better as ours. Yes, it looks a little bit better, but here what the people are doing, they apply filtered back projection to the image, and then they make the image better by learning this bad filtered back projections, and they compare it with the image they want to have. And in order to program or to learn this network here, they programmed or they learned it with 32,000 some hundred images. And for all these images, you have to do filtered back projection, produce a new image, compare it with the image you want to have. This takes a while. Moreover, it's operator dependent. We had a look into the net. We want to compare our method with this heavy method with many, many images, but it was in the net only for limited angle, for low angle tomography, where you have small angles, but we want to do this for limited angles now. So my poor guys went into their rooms and learned this network again with 32,000 different things because there was just a different operator, yeah? So, but for our thing, we don't need it. We can take the same thing because it's just a regularizer. So, okay, and you see it also in numbers of maybe I go to the spec somehow. Genau. And you see this also in quantitative numbers, that among these networks here, with these quantitative numbers like S and M, our networks perform very well. Okay, this is a little bit better, but only a little bit. So, and we took, for example, LPIPs, which is also a learned error measure here, these LPIPs from EFROS and SUN. So let's go to the next one. This is super resolution. Even easier, we'll take only one image here, and indeed these images come from a French RNR DFG project with colleagues from Bordeaux. And they went into the synchrotron. They buy time at synchrotron. It costs a lot. And these are 3D images. We have it of different materials. But of course, this is a very special material. And then we take just one image of these materials. It's very huge, 4,000 times 4,000 patches of this. We learn the regularizer. And then we can do super resolution. And you see it's better. For example, this point is much better covered in this area here, or even this area here is just in our method is much better, because this is it's related here. And here's another method which works with Wasserstein. This is from Johannes Hertrich again. This is these Wasserstein patch prior flows. Good. Okay. This is super resolution. So, and finally, what happens if I don't have any images? So far I have one image, 6 images. And now super resolution where I don't know perfect images. I don't have nice images. And then it appears that you can also learn this, but you can only do this, as we experienced, if you have natural images. Because for natural images, there exist papers which show that the patch distribution of natural images is self-similar across scales. So if you have a lower resolution, then the patch distribution looks similar. That's why we can learn a regularizer here. It doesn't work for our material images. We've tried with these material images. This doesn't work somehow. But it works for natural images. And if I would go into this, you would again see that our method gives the best results, also visually, but also in terms of quantities. And we compared it, for example, with these, I wouldn't say the word famous, but with the method of Mihai Irani. She's, I think, more or less the only one who can learn from very few images, and even from images which are not nice, which are sampled. And we can also do this, and our results are better. So, and this is just what we do with patches and what we do with normalizing flows. So now let me come to the negative parts of normalizing flows. And I have to say, these normalizing flows, the networks S&T we use, these are full networks. These are not convolutional networks. That's why it's not so good to use these normalizing flows for very huge images. But we have just 36 dimensions, that's completely fine. Up to 100 dimensions, that's completely fine. So, okay, so what's the drawback of these neural networks? These are diffeomorphisms. You have t and t to the power of -1. And it's completely clear that it's not possible that you can sample from such a distribution which has multi-modes. You see, it's a multimodal distribution from a distribution which has only one mode, because then you must have a very huge Lipschitz constant of this network. Otherwise, it cannot work. You cannot jump from this unimodal distribution to the other one. Yeah, it's a continuous guy. So, okay. So this will not really work, and at the beginning I was cheating you. You will get, if you have a moderate Lipschitz constant here, you will get samples within here, which is not very nice, because we want to produce such a distribution. So, and one way out is that to avoid, and there exist papers who really estimate the Lipschitz constant, not only for this normalizing flows, but also for other methods which use such push-forward things, yeah? And of course, there is a paper in our group from Sebastian Neumeier and Paul Hagemann, but there are very new papers. This is from the group of Julie Delon, for example, and they estimate that the Lipschitz constant of such guys must explode if you want to go from here to here. Not only for normalizing flow, this holds also true for generative networks, variational autoencoders, and blah, blah, blah. Yeah? So, okay, so one solution is that we use somehow stochastic steps within these normalizing flows, and these stochastic steps are such steps like MCMC, Markov-Chain Monte Carlo method, which push your distributions towards a distribution which, or towards a proposal distributions. You will see it in a minute. So, and what I want to advertise now is a unifying framework for which consists of so-called Markov chains for these stochastic normalizing flows. And this unifying framework, you see it here, will incorporate other things, other notations. Namely, you can describe Langevin layers, Metropolis-Hastings layers, variational autoencoders, diffusion normalizing flows, which are very popular now, by these Markov chains. And I will show how this works, yeah? And you can couple them within this framework. So, and this is what you can do then. This is your proposal density, this is your latent density, maybe sampled from the Gaussian. What you would usually get is, if you want, this is where you want to go, this is what you want to sample from. If you use it without the stochastic steps, you will get something like this, which is not really nice since you have additional samples here. And what you can produce by using these proposal densities, these stochastic steps, is here you take a usual normalizing flow, a stochastic step, usual and stochastic step, blah, blah, blah. You can really sample from this distribution. So let me start with this unifying framework. So, okay. What we need if we want to use Markov chain is a Markov kernel. So what's the Markov kernel? A Markov kernel is a kernel which maps from RD and the Borel-Sigma algebra of RD into 0, 1. And if you fix the second argument here, the set here, it should be measurable. If you fix the first argument, this is a probability density measure. Okay, this is a Markov kernel, that's fine. And by the help of these Markov kernels, you can now define distributions not only on RD, but also on RD times D by the following way. You take, this is now a distribution, if you write it in this way, of RD times D, and you take the Markov kernel at B, and you integral over A with respect to X. So this is now a distribution on R times R. So, and now I need special distributions, namely, if I have a distribution Px and a joint distribution of Px and Y, then there exists a unique Markov kernel almost everywhere, Py almost everywhere, such that Px times, in this construction here, the probability density of Y given X gives this joint probability. So, or with other words, if you have a look at this, this is now my Markov kernel. This X is equal to small x, this is this guy here. And this here, if I fix this small x here, then this is a probability density, density with respect to this argument. So, and now I can do this not only for one x and one y, I can build such Markov chain for a whole change of random variables, x0 to xt. And this guy is called a Markov chain. If I can describe, as if I have a Markov kernel, which shows me how to go from one random variable to the other one by introducing here these conditional probability density here, this Markov kernel. Yeah? So I take this Markov kernel, and by the help of this Markov kernel, I now go from x0, take the first Markov kernel, I get the joint probability between x0 and x2, next Markov kernel, and so on. And finally, I get the joint probability of all these random variables. So, how this helps? First step, I show you first how this helps with the normalizing flow, what it has to do with the normalizing flow, I explained you, and then I show how to introduce these stochastic layers. So, here is again my ordinary normalizing flow with these networks, these special networks which were invertible. Now I write this down with the help of a Markov chain. That means I start with a latent variable set, and now I apply my networks here, and if I apply the first one, I get a new distribution, I apply the second one, blah, 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 and so on. Final one, I get xt, so another distribution. So, and then I go this way back, I say, okay, this xt should later be near to yt. This is the distribution I want to sample from, I don't know. And then I go in the opposite direction. Remember, my normalizing flow is invertible. All these networks are invertible. And I can go in the opposite direction, starting from this distribution Px. Fine. So, and now I can say, okay, now this is my Markov chain now. The new random variable is given by take the old random variable, apply this network t of t, and you get the new random variable. Yeah? And so you go in both directions. So, And now what is the Markov kernel for such a Markov chain? If you have these variables here, these random variables, what is the Markov kernel? Which you have to know. And the Markov kernel is just given by a delta measure, which this network T here. And this is a deterministic Markov kernel. It's called deterministic Markov kernel. So, okay, now let's have a look at my loss function. This is the loss function from the previous slides. This was the Kullback-Leibler density or distribution between Px and this push-forward guy here. Good, and now I can show that this is exactly the same as the Kullback-Leibler distribution of the joint distribution of these variables here and these variables here. So this is the same. So I just wrote it down in another way as a Markov chain. So now the idea will be replace some of these steps here in this chain by stochastic steps. Make it a little bit different. Yeah? So this is the next step. Then I will no longer have this relation here that this is exactly equal. Here I will have that this is smaller or equal. Yeah? So, okay, now let's do this. Let's define these stochastic normalizing flows by the help of Markov chains. I have two changes now, one in one direction, one in the other direction. I have to give up this invertibility of my network. This will be not the case any longer. Yeah? So, but I have two Markov chains, one direction, the other direction. And what I want now is just what was on the previous slide. I want that the joint probability density function between my way in this direction and the way back, the Kullback-Leibler divergence of this should be the same. Okay, reasonable from what I did at the previous slide. So, and I want something about my probabilities here. I want that they have a density function. This is fulfilled for everything, for Langevin flows and so on, what I have on my slide. I want that I have these Markov kernels here so that I can go step by step from one part to the other one. And I want that my Markov or my probability measures here, I put a fixed x here, that these probabilities are absolutely continuous with respect to each other. So this is absolutely continuous with respect to this, and so on. Yeah, this is a big difference what we had in the literature. In the literature, there exist these stochastic things and there exist some concepts here, but they want that all conditional distributions have densities and that they are absolutely continuous with respect to the Lebesgue measure. This is different. Here they are absolutely continuous with respect to each other. It's different from saying that this guy is absolutely continuous with respect to the Lebesgue measure, because the layers we have here, these ENN layers, Markov chain Monte Carlo layers, and so on, they are not absolutely continuous with respect to Lebesgue, but absolutely continuous with respect to each other. And this is something we had yesterday in the dinner. You called it undefined mathematical objects, UMDs, Anders said it. If you have a look into these conference papers, there are many UMDs, something which is really not defined in a mathematical meaningful sense. So, and I think the meaningful sense are Markov chains here. You cannot divide two delta distributions at different places or something like this. The idea is fine, but the math is not correct. So, good. Here is my loss function now. I have to rewrite this loss function with respect to this probability. F is just the Radon-Nikodym derivative between these probabilities. And now you have to believe me that I can compute these guys, this Radon-Nikodym derivative, for all these layers I suggested you. This is for the deterministic layer. This is for normalizing flows. F, the Radon-Nikodym derivative, is just 1. I can write these quotients down here. This is just this, and I can learn the T. This is here stochastic layer, Langevin layer. I show it in a minute. Here's nothing to learn in the stochastic layer. The stochastic layer is just for pushing your distribution in the correct direction, yeah, to the proposal density. And these are the other layers, variational autoencoders, diffusion layers. I cannot go through all these layers. The talk is much too long then. I just show you the Langevin layer, okay? Okay, what is this Langevin layer? The Langevin layer is, you can write it as a Markov chain where you get the new probability or the new random variable in such a way from the older random variable. From xt minus 1, you get xt in such a way. And here you have such a, this is Gaussian noise, you have here such an ut, and ut is the logarithm of a so-called proposal density. So, and for such a chain here, you can really write it down with the Markov kernel, and the Markov kernel is a normal distribution where the expectation value depends on this x, and this is a probability, it's a Gaussian probability, and this is just the measure which you take in for this transition kernel. So this is a measure with respect to this argument. So, and this Langevin dynamics comes from this is one, what I wrote down here, this is one explicit Euler step, one discretization of the overdamped Langevin dynamics, which is a stochastic differential equation, and if you discretize it by Euler forward, you get such a discretization step. So, and if you assume now that your random variable have a density, this is exactly the same if you write this down, or you can write this equation down with respect to the density, then you get a usual partial differential equation, and this is just the density of this random variable, yeah, and you can compute this. And yeah, here I know some people in the audience who know that this is the Wasserstein gradient flow with respect to the Kullback-Leibler divergence. And this pushes, if this tau goes to infinity, it pushes your density into the direction of your proposal density. And this helps a lot if you have different modes. So, and we can put such steps between our usual steps of the normalizing flow. You can do this with MCMC layers, and you see, I always wrote down the transition kernels here, the Markov kernels. You can do this with variational autoencoders. You can reinterpret the variational autoencoders in a nice way as a Markov chain. You can do it with diffusion layers. It's just a Markov chain with different kernels and so on. So again, I want to solve inverse problems, and so far I just generate distributions. So, and if I want to, so far the stochastics comes from the noise up to now in my talk. Now I want to have also random variables x, which I give into my system, into my forward function. So, and then I have to say, I have only 5 minutes, so I must hurry a little bit up. I can also define conditional stochastic normalizing flows, which depend on the input of the inverse problems. Yeah, and it looks quite similar, just I have to introduce an additional variable here, yeah, just the output of my inverse problem. So I can do exactly the same thing, and then I can try if it works, and I have different examples here. The first example is I sample from a distribution, or my Px is just a Gaussian mixture model. What I want to get, or where I want to sample from, is now not from Px, but from Px given a y, because I want to solve an inverse problems. But for mixtures, for such Gaussian mixtures, you can write this immediately down. If your model is like this, it's a linear model here, as a linear inverse problem, you can write the posterior down with respect to these operators and the other ones. So you know what it is. We have something, a ground truth, where we can compare our method with. So, and then I just show that something is better here. We took a 100-dimensional Gaussian mixture model in 100 dimension, and these are just the marginals with respect to, I think, marginal 20, 50, and 100 or so. And then you see, if I just apply here some normalizing flow, you see what happens. You cannot cover these modes here. We have 5 modes in the Gaussian, the orange guys, and you will produce samples within. That's not possible with a normalizing flow where you have a good Lipschitz constant. But if you introduce some stochastic layers, you see things become better here. You have really nice results here where you can really cover these modes, these 5 modes in our Gaussian, in a very good way by using, and just the best one was here, the Mahler layer. This was Markov chain Monte Carlo in combination with Langevin dynamics. So we did it also for practical things together with the Physikalisch-Technische Bundesanstalt in Berlin with so-called line gratings where we want to estimate something. It works, also I go just through this, but I have to come to conclusions. I did 2 things in my talk. I thought that normalizing flows are a powerful tool for generative approaches if the dimensions is not too large. We can solve inverse problems in a nice way. We have very good regularizers for these inverse problems. We can do something I haven't shown here, namely uncertainty quantification, at least numerically. For this, you need really these Wasserstein flows. I haven't shown this in my talk. Again, we have this power of patches. It's not necessary to, you can use it for other inverse problems. Yeah, diffraction tomography, MRT, what you want. If you have correct images, you can use the same thing. Learn the regularizer. So, and maybe you can also use features here. Yeah, that you learn the features in the same way, features of something. So, and then, yeah, it works for different inverse problems. Normalizing flow has a limited expressivity, that's proved. So, and yeah, stochastic normalizing flows can help to improve expressivity. I show how to set up such normalizing flows. Many concepts fit into this Markov chain mathematical framework in a very sound way. I have shown this. I have no estimates that this normalizing flow really works, yeah, that it really can separate these modes. So there's no, this is just how to set it up. It was enough to show that all these Markov kernel exist, blah, blah, blah. I have no theoretical guarantee. So, okay, these are the papers. The first 3 papers are about these patch things, about normalizing flows, and these here are some other papers. This is about algorithms, in particular Palm algorithm, and from an inertial stochastic point of view, and these are about Lipschitz constant algorithms, for example, in relation with plug-and-play algorithms. So, and finally, let me take some advertisement. First, thank you for your attention. 2 advertisements. We have such a German-French conference. I think I'm the only German here. So, this is the MIA conference. It is every second year at the Poincaré Institute in Paris, and the other year it's in Berlin, so next year it's in Berlin, and I want to advertise this conference a little bit. We have a lot of nice speakers, and I also want to advertise that there is a MIA prize. It's 1,000 euro, not very much, but a little bit for the prize winner. If you have a very good PhD, or had a very good PhD, you can submit also your own PhD. You need, I think somebody has to write something about it, that it is a nice PhD, and then you can win this prize. Yeah, and we have many nice speakers for this conference, not only from Germany and France, but also, for example, Tom Goldstein from the US and many others. You see it here. So, yeah, it's an announcement for this conference. And normally I don't make an announcement for PhD positions, but yesterday somebody asked for it, so there will be an announcement. I will have a postdoc position and also a PhD position in imaging. This PhD is also nice. It's together with the big hospital Charité in Berlin, which is very famous and makes very good research there. So I just do it because yesterday there was a job question, so now a job advertisement. So I'd like to thank you for your attention.